Hi class, this is the class video for Friday, January 22nd. I'll be going over some key calculations and the important points of this class. So first of all, I shared the accepted value for the heat of crystallization. Nice job. Most of you got quite good values considering that this is an experiment that has a lot of sources of error as well as assumptions. Then we did this FRQ, and I'll go through this briefly. This FRQ is an actual FRQ from the AP exam. And we have this setup where a beaker of sand is being heated by 180 degrees Celsius. So we're increasing the temperature by that much. And so in part A, they asked for the amount of heat energy. So this is Q. So use our favorite Q equals MCAT equation. And we plug in for the mass, our 1650 gram beaker, times our specific heat, times our temperature change, which is 180 degrees C. And when we calculate that out, we get a value of 241,000 joules, or 241 kilojoules. And then the next part, they give you a sample data table, and they ask for the number of moles of butane that was used. Okay, so here is the butane inside of this burner. And here is mass data for the butane burner before combustion and after combustion. So presumably the difference between these, when we subtract these numbers, will give the amount of butane used. So when we subtract here, we get 7.06 grams of butane. And then we would have to change that. Oh, that is an H10 there. Change that to moles by dividing by the molar mass. So we take our 7.06 grams, divide by the molar mass of butane, which is 58.14 grams per mole, and we get 0.121 moles of butane. Now notice that this question says to report your answer with the appropriate number of significant figures. So this is the sig fig question on the exam, and that will be a point. So pay attention if you see that. Sometimes they do specify which question is the sig fig question. Other times they do not. Then for parts C and D, we have to use the thermochemical equation to figure out the amount of heat energy produced by the combustion of butane, assuming that it's this many moles that's being used up. So 0.121 moles of butane. We can see from this relationship that this many kilojoules is produced for every 1 mole of butane. So I can use that relationship. So negative 2659 kilojoules for 1 mole C4H10. And that will cancel out my moles, and I will get negative 323 kilojoules for my heat energy produced from the burning of this many moles of methane. And in part D, the student claims that some heat energy produced by the combustion was lost to air. Do the answers in part A and C support the student's claim? Explain. So from part C, we can see that negative 323 kilojoules was produced by the butane. So this flame, this burning, is giving off 323 kilojoules. So that heat is supposedly rising and going into the beaker. However, from part A, we can see that only 241 kilojoules is required, okay, to heat the sand to 180 degrees. So clearly, if the butane burning is producing this much energy, but it only requires 241 kilojoules, some of the heat is being dispersed into the air, okay, is being lost to the surroundings. Perhaps some is going into the thermometer. Perhaps some is going into the butane burner and being transferred into the burner here. So we are losing about 80 kilojoules of heat there. Okay, so you would write an answer, yes, I agree, and add a explanation sentence, and this is in the annotated slides. I'm just not going to take the time to write it out here, but saying something to the effect of the butane's producing this much energy, but it only requires 241 kilojoules of energy to heat up the sand, so some of the heat is lost to the surroundings. All right, so the next topic is using bond enthalpies to calculate delta H. So far we've calculated delta H from calorimetry. We can take this and divide by the moles of a reacting substance to get the delta H, or we can just get it directly from a thermochemical equation. And now we're going to learn to use these bond enthalpies, which are energies required to break covalent bonds, to calculate delta H. And these are average bond enthalpies, so averaged over several different substances that have these bonds. And there's a table here first of single bonds, and then multiple bonds are down here. And notice how strong this nitrogen triple bond is. The key part to remember about bonds and bond enthalpies is that when we break bonds, energy is required. Okay, to break the attractive force apart, we have to put in energy to break those bonds. Forming bonds, on the other hand, releases energy. Okay, by forming that attractive force, you bring the substances down to a lower potential and energy is released. So I went over this practice problem, so I'm going to redo this. And what we want to do is figure out what bonds are broken and what bonds are formed. And this sigma means sum. Okay, so from math, sum. And we need to get the sum of the bond enthalpies of the bonds broken minus the sum of the bond enthalpies of the bonds formed. So here I'm going to just list out what's broken and list out what's formed. And when we have just these substances like this, we need to draw out some Lewis structures in order to figure out which bonds are being broken and formed. So here I'll just draw out some rough structures. And HCl looks like this. So I can see that here, right, here is methane, and in the products, one of the CH bonds has changed into a CCl bond. So we are going to break, I'll do that with a squiggly line there, and we need to break this bond here. We need to form this bond, and we need to form this bond. Okay, so here we're breaking a CH bond, and we're breaking a Cl bond. Here, a CCl bond is formed, and an HCl bond is formed. Then we can just find the bond energies and calculate. So now we have to list the bond energies for each of these bonds and calculate. So first of all, delta H, okay, is going to be the sum of the bonds broken. So CH is broken. The bond enthalpy is 413 kilojoules per mole, plus a Cl-Cl2 bond, 242 kilojoules per mole. And then we have to subtract off, that's a big subtraction sign, the bonds formed. So CCl is 328 kilojoules per mole plus 431 kilojoules per mole. So then just summing up over here, we get 655, and summing here, we get negative 759, and subtracting, we get negative 104 kilojoules per mole. This is an exothermic reaction, which means that the bonds formed are stronger than the bonds broken. We did this other example in class, which was very similar to the previous one. And you should try it on your own to review, but the answer for this is negative 104 kilojoules per mole as well. Our next example, I asked people to do in breakout rooms, and the answer to this comes out to 20 kilojoules. Okay, so the answer is 20 kilojoules. Now, another technique, if it is difficult to see which bonds to break and form, one thing that you can do is just break every bond, form every bond, and list them, and then get rid of the duplicates, right? If you have to break and form a bond, then nothing's changing with that bond. So you're breaking it and forming it back. So if we can look at every single bond that's broken here, and let me use some different color ink to emphasize what's getting broken. I can write down all of the bonds that are broken here. I'm showing what's broken, and I'm gonna make this, instead of put a 2 here, I'm gonna actually draw another molecule of HBr. Same here with the H2S. Make another H2S. We can see that these are the bonds that need to be broken. So we need to break 2 SH bonds. We need to break 1, 2, 3, 4. Oh, and I missed a CC in the middle as well. So 4 CH bonds. We have to break 1 CC bond. And we need to break 2 CS bonds as well. And then over here with the HBr, we need to break 2 HBr bonds. Now we got to look at what we're going to form back. Let me use a different color for that as well, maybe blue. What bonds have to be formed back after we've broken everything? Well, it's all of these bonds here that need to be formed back. So we'll have to list those out. So we'll need 2 CBr bonds, 2 CC bonds, 1, 2, 3, 4 CH bonds. Let's see if we're missing anything else in this compound. I think we're good. And then we have to make 4 SH bonds. So then looking at our list, which bonds are broken and then reformed? Well, those have not changed if that's the case. So I'm going to go ahead and cross out any bonds that appear to be broken and then formed. So my 4CH, we don't have to break those because they're going to get reformed here. All right. Oh, and this should be 1 CC, not 2 CC. This CC is also not changing. Okay. And then if we look here, there's 2 SHs, 4 SHs. So 2 of those are being reformed. So we can have 2 SHs here. So these are the bonds that are broken and formed. So now we can go and plug these into here for delta H. So delta H, I need to do 2 times my HBr. So 2 times 366. Okay. Plus, and let me put brackets around here, 2 times my CS bond, 259, minus the release in energy from the bonds formed, so 2 times my CBr, so 276, plus 2 times, yep, I redraw that, it looks messy, plus 2 times my 339 for the SH bond. And then be careful. Probably the most common trip up is, okay, having a problem with the signs. Okay, but if you calculate everything and make sure your signs stay what they're supposed to, you should get 20 kilojoules. So here's more questions here that you can practice. And I will do out letter C as another example. So C, we have H2O2, so we have to draw out some rough structures, and it does require you to know a little bit about what the structures look like, and if not, you will have to go do the Lewis structure. Here, I'll even put in my dots to be a good student and show all my dots. So 2H2O2 is changing into 2 H2O molecules. You should know that they look like this. And O2 has a double bond. All right, so let's look at what needs to break and what needs to be formed. So breaking side, break. Looks like we're going to have to break our peroxide in half. Okay, looks like we need to somehow get our oxygen, our hydrogens over onto this part right here. Okay, so we need to break this bond, attach a hydrogen to the OH, and then we're going to have to form that O2 bond. Okay, so we got to break that. We got to form the bond right there, and we need to form this double bond. Okay, so break 2OO and 2OH. Then form 2OH, okay, and 1O double bond. Okay, so hopefully, so now to calculate delta H, I can also, I can just cancel these out because you can see that they're breaking and forming. So my delta H of reaction is going to be 2 times my OO bond, which is going to be 2 times 146 kilojoules per mole. And then subtract off the bond that's being formed, which is 1 double bond. And that double bond is 495 kilojoules per mole. So then when we work this out, we end up with a value of minus 203 kilojoules per mole reaction. So we can get delta H reaction using our bond enthalpies. So moving on to the next topic, another way to find delta H of reaction, we can use something called enthalpies of formation. Now, these enthalpies of formation are coming from when a compound is formed from its elements, the elements that make up that compound in their standard states. So these are a set of conditions, standard state conditions, and that refers to 1 atm and 25 degrees C for solids and liquids. For gases and solutions, it's slightly different. For aqueous solutions, that's 1 molar, and for gases, it is 1 atm. But either way, all of these are in their standard state when they're at these conditions. So the standard enthalpy with the little circle now means that it's the enthalpy measured when we're in the standard state. Everything's in the standard state. And that's what that little superscripted circle means. And then the standard enthalpy of formation is when we form a compound, 1 mole of the compound from its elements in their standard states. So if there's more than one structure for a compound or an element, we use the most stable one. Sorry, just for an element under standard conditions. So for carbon, we use graphite because graphite is the most stable form of carbon at standard conditions. And one of probably the important things, not probably, an important thing to remember with enthalpies of formation is that if you're in the most stable form and you're at standard state, that enthalpy is 0. Okay, the enthalpy of formation of carbon graphite is 0 because no energy is needed to convert it to its standard state. O2 gas, 0. Okay, so any element in its standard state, the heat of formation is 0. So using delta HF, heats of formation, okay, that's what these are, heats of formation or enthalpies of formation. There's an equation, and this is on your equation sheet under thermodynamics. So this equation says that if you take the heats of formation of the products times their coefficients and you sum them all up, then you subtract off the heats of formations for the reactants times their coefficient, okay, the sum of that, you will get the heat of reaction by subtracting the two. These heats of formation can be found in your textbook on page 1100, okay, or here are 2 other tables that you can use. I'm guessing that the textbook is probably going to be the easiest one to use. It'll be readily accessible, so that's what I would do. Okay, let's do a couple for practice. So if we take a look here, we'll try B, and I will also do A. Starting with A, we can use the values from Appendix C and figure out the heats of formation for these particular substances. Okay, and then we go ahead and use our summation formula to find the delta H. So here we'll start off by writing delta H reaction is equal to the sum of the heats of formation, the products, minus the sum of the heats of formation of the reactants. Okay, so starting out, we have for the products 2 moles of SO3. So I'll do 2 times. My value for the heat of formation for SO3 is minus 395.2 kilojoules per mole. Okay, minus my reactant. So we have 2 moles of SO2. So I need to put 2 times my SO2, which is minus 269.9 kilojoules. And then sum up my oxygen, but notice this is in its standard state. It's an element. Okay, element. So whenever you see an element, see if it's in its standard state. That means its heat of formation is 0. Makes it convenient. All right, so now, again, be careful with your signs. Okay, make sure that you get your signs correct, and you should end up with negative 196.6 kilojoules. So I'm also going to do letter B for you as another example. So in letter B, we've got magnesium hydroxide breaking down, decomposing. So again, here we need to get our delta H of reaction by finding our heats of formation of the products and our heats of formation of the reactants. So looking up our values in our table, we need 1 mole of MgO this time. So the heat of formation for MgO is minus 601.8 kilojoules. And then we need to add on, because here's our summation here, 1 mole of H2O, the heat of formation for 1 mole of H2O. So that's going to be minus 285.83 kilojoules. Okay, so those are our products. Let me put some brackets around there to keep that separate. And then our reactants are magnesium hydroxide, 1 mole of that. So that would be minus 924.7 kilojoules. And so again, be careful with your signs, okay? And make sure that you get your signs correct. And you should get 37.1 kilojoules as the answer for letter B. So here's another practice problem that you can try, and here's the answer right here. And here's another practice problem. Now this one is slightly different, so I will go over this. So in table 5.3, we have our enthalpy values, and it is asking for the standard enthalpy of formation of CuO. So instead of finding the delta H of reaction, they're actually giving that to us, but they want us to find the heat of formation of CuO, the standard heat of formation. So let's set up our equation just like before. Delta H reaction is equal to the sum of the heats of formation of the products minus the sum of the delta heats of formation of the reactants. So plugging in here for our products, we have copper solid. Well, that's an element in its standard state, so that's going to be 0 for the heat of formation. And then we have one mole of H2O liquid. And so for that, we're going to use our heat of formation for H2O liquid, and that is a value of minus 285.83 kilojoules. Okay, so plus, I need a plus sign there, because we're summing these, and then minus our reactants. Okay, so again, here we see an element, so again, that's going to have a heat of formation of 0 for the H2 gas. And then our heat of formation of CuO, that's what we're trying to find. And you can see it's not in the table here. So delta H CuO. And that is going to be equal to our delta H of reaction. Notice we have this value this time. Instead of calculating it, we have this, and we're calculating one of the heats of formation instead. So here, if I just write this out again, we have that minus our delta H CuO is equal to minus 129.7 kilojoules. This is also kilojoules. And so moving my 285 over to the other side, I need to add 285.83 to both sides. But then remember that this will leave a negative sign here. So we also have to take the negative of this to get the value over here. So right now we have negative delta H F CuO is equal to this value of positive 156.1 kilojoules per mole. But since we need to move that negative over, the delta H is equal to negative 156.1 kilojoules per mole reaction. Okay, so this is another thing that could be asked. You could be asked to get the heat of formation instead of finding the heat of reaction. So then we went into Hess's law, and before we could learn to use Hess's law, just a review of these enthalpy manipulations. Remember that if we have a reaction and then we reverse the reaction, we flip it, then we change the sign of the delta H as well. And then the second manipulation is if we divide or multiply a reaction by some number or a factor, you multiply or divide delta H of the reaction by the same number to get the new delta H for the new reaction. So here, if I multiply this top reaction by 2, that means that I need to take my delta H and multiply that also by 2 to get negative 2,734 kilojoules for twice this reaction. So basically, whatever I do to this reaction, I do to the delta H. And in one, if I reverse the reaction, I change the sign. So Hess's law says that if you have a series of reaction steps and you can add them together to get some particular reaction, some specific reaction, you do the same with the delta H's for those steps. If you add the steps, you can add the delta H and get the delta H for your overall reaction. So this is useful when you have a reaction that cannot be measured easily in nature and as an experiment in the lab, and it allows you to calculate the delta H without actually having to perform this overall reaction as written. So let's give one of these a try. And so I gave this as an example in class. So here we have 2 reactions, and it's saying that, okay, using these 2 steps above, calculate the enthalpy for this combustion reaction. So if we take these 2 reactions and manipulate them to turn into this, that's what we want to do. We want to get the pieces of these overall reaction parts from the steps. So the first thing I see is that I have carbon solid on the left. And if I look at step 1, carbon solid is on the left. So I'm going to take step 1, I'm going to rewrite it. And since I kept this exactly the same, my delta H for step 1 is going to be exactly the same. And then I look, okay, my O2 is in 2 places. So I'm going to deal with my CO first because I'll leave this for last and hope that it comes out once I get my CO into place. So I look at the second reaction because I've already used the first, And I look at that second reaction and see, oh, okay, so CO is a reactant here, but in my target equation, okay, think of this as your target reaction. I need to get my carbon monoxide onto the product side. So I'm going to have to flip this reaction. So I can flip number 2. And if I flip number 2, I end up with CO2 as a reactant going to carbon monoxide gas plus half O2. Okay, so then I can flip the sign of my delta H for number 2. Because I reversed it, I also flipped the sign of delta H. All right, so now I'm going to add these reactions together. The way to add reactions is everything on the left-hand side of the arrow gets added together. So C solid plus O2 gas plus CO2 gas. And then everything on the right gets added together. So I have CO2 gas plus CO gas plus a half oxygen. All right, so then I can cancel anything that appears on the left and the right. So my CO2 is going to disappear. Okay, and then I can also combine terms. I see O2 on both sides. Okay, so I want to get O2 on just one side. And so I can get rid of my half O2 over here by subtracting it off. Should always end up with positive numbers of things. And then we can just combine here. C solid 1 O2 minus a half O2 gives a half O2. And yields, okay, this cancels out there, and yields carbon monoxide gas. And so you can see that this matches the target, right? This is the reaction we want. Okay, so you can see that if I add these 2 steps together, I get the target. So all I have to do now to get the delta H for the target reaction is to add my delta H's. So adding those together, I end up with minus 110.5 kilojoules per mole reaction. Okay, I just needed to do this. Let me write out the actual steps that I did. So minus 395.5 kilojoules plus 283.0 kilojoules. That equals my 110.5 kilojoules per mole. So that's Hess's law, taking these pieces and manipulating them so that we get the overall target reaction here. Okay, so we'll do one more example. This one you can do on your own. The answer is here. I also did this reaction in class. You can take a look at the answer, and in the notes, the answer is also on the slides. But I'll go over how to do 5.66 because here now we have 3 steps. Okay, this is a little more complicated. Here's our target. We need to find delta H for this. So if we can figure out how to manipulate these steps and adjust delta H to add up these steps and get the target, to figure out how to change these to get the target, then we can do the same with the delta H's of those steps, and we can get our delta H for the reaction. Okay, so look at your target. Okay, the target needs N2O gas on the left. Which step here? Let's number our steps, 1, 2, and 3. Which step has N2O on the left or N2O anywhere. So that would be step 3, right? We can see N2O gas on the reactant side, so it's on the correct side of the arrow, but it is 2 N2O and not 1 N2O. So I would have to take that reaction and multiply it by 1/2. And so if I multiply this by 1/2, I need to multiply my delta H by 1/2. So let me write that out below here. I'm going to write out my steps and then add them up at the end to make sure that I get this target equation. So if I take 1/2 times this reaction, I will get N2O. 1/2 times 2 is 1. Yields 1/2 times 2 is 1 also, 1 N2. And then 1/2 times O2 gives 1/2 O2. Okay, and the delta H for this is going to be 1/2 times 163.2. So let me just get that number on my calculator. I get minus 81.6 kilojoules. Okay, because I took 1/2 times this, since I took 1/2 times this reaction. All right, so I've got my N2O in the right place now. Now, my next thing that I'm going to look at is my NO2. Okay, my NO2 appears on the right-hand side of equation number 2, but it's on the left in my target. So I need to flip this. I need to flip this around. And there's also only one NO2 here, but there's 2 here. So I need to also take it times 1/2. So I'll have to do the same to my delta H. I need to flip this, so I'm going to have to make this positive, but I will also have to take this times 1/2. So if I flip this around and take it times 1/2, let me put a 1/2 in front of here, I'm going to end up with 2 NO2 times 1/2 is going to be 1 NO2. And then on the right-hand side, I'll have 1/2 times 2 NO. That will give me 1 NO gas. And then 1/2 times O2 gives me another 1/2 O2. Then my delta H is going to be plus 113 times 1/2. So that will give me 56.55 kilojoules. Okay, so we've got my N2O in place. I've got my NO2 in place. What about my NO? Well, we see 1 NO here, but we need 3. So looking at number 1, I see that there's 2 NO on the product side. If I add 2 NO to that, I should get 3 NO. So I'm going to keep number 1 the same. Just write it down. And that will be the same delta H. I don't need to do anything with that. And so now let's check and make sure that when we add these, we get our target equation. If we don't get our target equation after adding these, we have done something wrong. Or maybe we messed up something in writing down these steps. So let's see. N2 appears on the right and the left. Actually, let me just write this out just to give a little, instead of cutting some steps. Okay, everything on the left is going to be added up onto the left-hand side. N2 plus O2, right side of the arrow. N2 plus 1/2 O2 plus NO plus 1/2 O2 plus 2 NO. So I've added everything together. Let me see what appears on both sides. N2 does. Okay. O2 does. This comes out to 1 O2, so that's going to cancel that out. And then these two add together to make 3 NOs. So after adding, we get this. And guess what? That is our target equation. We got it. Okay, so we manipulated things correctly to get our target. So now all we need to do is add the delta H's here to get our delta H for our target equation. So adding these together, we end up with plus 155.7 kilojoules per mole reaction. Nice. Endothermic. Okay, so hopefully that gives you a good overview of what we did today. We covered Hess's law, we covered heats of formation, we covered bond enthalpies, and we did some review of calorimetry and heats of reaction thermochemical equations. Okay, and please email me if you have any questions.